So I guess the session is recorded, and we can officially okay. So and we can officially start the session. So welcome everyone into the poster session 1 at XC 2022. So my name is Elena Sherman. I'm one of the posters co-chair, and I'm going to also chair in the session. So we're going to have 4 presentations today, and the format is 5 minutes for presentation, and if you have questions, going to be up to 3 minutes for questions. So with that, we're going to start with Kevin Alano, and he's going to present his poster on program translation using model-driven engineering. So go ahead, Kevin, share your screen and you can start the presentation.
Okay, welcome everyone. Good morning or good evening. It's early morning for me. So the point of this work is to deal with program translation, for example, translating from JavaScript to Python or Java to Swift.
Kevin, sorry, did you start your slides sharing or not yet?
Yes,
because I didn't see any slides yet on the screen.
Let me double check that again. I thought I did.
Yeah, and who also cannot see it. Here we go. Yeah.
Okay. Is that still visible?
No.
I see. So when I switch to full screen, it's not visible. Yeah. Let me just keep it as it is.
Yes. Sorry. Whatever works.
Yeah. It doesn't make any difference whether it's full screen. So yes, the challenge is to translate from one software language to another. Now, because there's so many different languages, it's obviously a huge effort to create translations from one individual language to another different individual language, and so the way that we've resolved this is to translate from a programming language to an intermediate language, and then from the intermediate language to the new target language. So we use as an intermediate language the UML OCL standard, the international standard for model-driven engineering. And the advantage of that is that there's many model-driven engineering tools that already do the forward engineering from UML OCL to some other language. So the main effort here, the main new work, is to abstract from a programming language to UML OCL. So that's what I've focused on. And how that's done is to use a parser, of course, and we've used Antler, which covers a very large number of software languages. And at the moment, we're starting from C, Java, and we've just done JavaScript, at least a large part of JavaScript as well. That gives syntax trees, which are then processed by our abstraction language, which is a simple rule-based language for processing abstract syntax trees and producing text. And the text it produces is a text version of UML OCL that represents the semantics of the original source program. That also uses some libraries for facilities like exceptions and iterators and files and so on. Combining that together, we can then generate code in a number of target languages. Now, other MDE tools could be used for the forward engineering. We happen to use Agile UML because that's what we developed. What do these abstraction rules look like? Well, they're rewrite rules. So you start off with an expression in the programming language, like a conditional expression that's then turned into the equivalent in OCL UML. And then in forward engineering, you translate that into whatever is a conditional expression in another language, like Python, for example, has a different syntax yet again. So how did we evaluate this? Well, we looked first of all at Java as the source language, and then C, and then now more recently JavaScript. These abstraction mappings are reasonably small, about 2,000 lines of code. The first one took a lot of effort, and now it's developed, we've used progressively less effort on other languages. C, JavaScript was done in about a month. Now, you can cover a lot of the language, and in principle, you could cover all of the language, the grammar rules. Perhaps the big problem, though, is libraries, because languages like Java have very, very large libraries, and so only a relatively small amount of the core libraries are covered at the moment. How do we check that these are correct translations? Well, we do tests. We do a number of tests for a set of example cases, and we check that the results of the tests are the same on the original program and the translated program, and we compute the percentage of the test results at a degree. It's called computational accuracy, and it's been used by other people in this field. Use 100 cases for the Java 6.7 abstraction, and for 70 cases for C, and 85 for JavaScript. The bottom line here is that the accuracy is pretty good from Java. It's over 90%, depending on the target languages, and that's covering the main language libraries for Java. For C, the percentage is a bit lower because there are certain semantic peculiarities in C which are not necessarily compatible with other languages like Swift. These languages, you notice, they all have pointers, but the Swift pointers and indeed the Go pointers are somewhat different to C pointers. So the translation of pointers is here the big kind of obstacle. But our results are still pretty good compared to existing approaches, heuristic approaches like Java to Python, or machine learning approaches like Transcoder. Those are significantly lower than what we've done here. Machine learning is probably currently the leading approach, but it has significant problems because you need very large data sets of program examples, and also there's no guarantee about the result. It's an implicit translation, implicit rules are learned, and inevitably there are some errors in that process. So we've shown that this approach to program translation with abstraction followed by forward engineering can actually work. And one advantage is that the users could customize the translation rules because it's a simple text substitution language. So if they want to define a different translation or customize the translation, then that's not, in principle, it's not too much effort. Now, machine learning, as I say, would be a nice thing to have because it does reduce the manual effort of writing these abstraction and translation functions. And we're looking at symbolic machine learning to learn precise abstraction mappings. But that's more, future work and more speculative. At the moment, we're defining abstractions manually. Okay, so that's the presentation.
Thank you so much. So we can kind of give applause. There is a nice icon you can give applause. So, so with that, we can start answering questions. I'm not sure you guys can just put question on chat, or if you can, I'm not sure if you can unmute yourself, and if it's possible. Yay, nice applause. Thank you. Okay, I can start with the question, Ken. So what's how are you extending this work right now? What your plans? Because it's just supposed to kind of your preliminary work.
Yes, well, one thing is language coverage. One gap that I want to fill in the case of Java is dealing with URLs, remote files, the whole kind of processing that's needed for connecting across the web and dealing with remote files, also databases. So we have some file abstraction, but that file abstraction only deals with local files. and then looking at other languages, and Visual Basic is something which is particularly of interest in finance.
Mm-hmm.
And then finally looking, as I said, at machine learning to reduce the manual effort of creating the abstractions.
Sounds great. So if there is no other question, we can move to the next presentation. So once again, thank you so much. And good luck on
question.
Oh, okay, question. Okay.
Hi, sorry to interrupt, and apologies if this was already answered, but I was kind of curious whether you could see such approaches being applied to things like documentation, to kind of like, sorry. So I know that UML can be very helpful for documentation, but would you ever consider adding additional layers on top of the UML to serve that purpose? Does that make sense?
Do you mean to create documentation?
Yes.
Or, yeah. Okay. Yeah, in principle, you could generate anything from the forward engineering side. The difficulty is producing the abstraction. One thing I should say about Antler is it discards comments, so the comments in the source program are discarded. Now that might be a problem for certain people, but that's just the way that's just the way the parsing does. In principle, I suppose you could extend to incorporate comments and then incorporate those comments as notes in UML and then regenerate them. But at the moment, comments are discarded.
Okay. I think there's other question in the chat, and maybe Kevin can answer it offline because we need to move on with the presentation. So, okay. do I have Michael Lin here? Because no. Okay. So then the next, Jenny, you can take it over then.
Great.
So Jenny is going to present the presentation of a poster named Toward Missing OS Skills from GitHub Activity. So take it over. Share your screen. It's all yours.
Okay. Sounds good. Give me 1 second to get this started. All right. Okay. Can everyone see my screen? Obligatory confirmation.
Good. We're good.
Yep. All right. Sounds good. All right. Cool. Well, today I'll be talking about our poster, entitled Towards Mining OSS Skills from GitHub Activity. This was done in collaboration with some amazing collaborators from Microsoft Research, namely Drs. Thomas Zimmerman and Danae Ford, while I was an undergraduate at the University of Washington. So without further ado, let's get started with some background. So when we're talking about open source software development, we think about these OSS teams that require really diverse roles and even more diverse skill sets to ensure that the development of the OSS is a well-oiled machine, ranging from maintainers to even documentation writers. Separately, detecting skills can be used to be applied to problems in software engineering and open source software, such as predicting technical roles in OSS communities or recommending individuals for jobs. However, prior skills detection methods really focus on detecting technical expertise, like skills in a particular programming language. However, this does not necessarily address soft skills. And this is notable because soft skills are really crucial to OSS development and software development, as shown from prior work. And so this work that we did really focuses on how are we able to detect skills that are relevant to OSS development, including both soft skills and hard skills. So our approach was really to identify relevant measurable activities or cues that correspond to specific OSS-related skills. We called these particular measurable activities called signals. And these signals are really drawn from GitHub Activity. So some potential data sources that we could look at are, markdown files or activities surrounding issues and PRs. Pull requests. So just to kind of ground this in concrete terms, an example of a signal is if we're looking at proficiency in Java, we might look at the number of lines of code written in that language. For communication, we might look at the toxicity score of GitHub comments to ensure that people are using welcoming and open and inclusive language. So let's take a look at how we exactly implemented this particular approach. First step is really to identify relevant OSS skills and signals. So this was done through a literature review, looking at papers in software engineering expertise, social factors of open source software, and finally mining OSS activities. We then validated these skills and signals that we extracted from a literature review with 3 open source software community experts. This yielded 4 total skills that we're going to be looking at for the rest of this presentation. 1 is teaching others to be involved in a project. 2 is showing commitment to the OSS project. 3 is being familiar with OSS practices. And 4 is having knowledge in a particular programming language. So what we did is, given these 4 skills, that I just mentioned, we are able to detect them and their signals in a tool that we call Disco. Disco is a Python tool that queries GitHub APIs and GHTorrent to mine signals. And the way that Disco works, what it does is it takes a GitHub username and then outputs skill ratings from 0 to 5 for the 4 skills that I mentioned before. Here, 0 represents not having any experience with the skill, while 5 represents having high proficiency. So the way that Disco works under the hood is that it first mines signals and then takes the proportion of the signals present to compute the skill ratings. If we look under the, specifically at how we calculate these skill ratings, what we do is we have a very simple piecewise function that uses the proportion of signals present for each skill. So this is a rather, simple and straightforward way to kind of determine or generate skill ratings. And so to evaluate such a tool, we have a survey. One part of the survey was really dedicated to evaluating the relevance of the skills that Disco detects. And then we also have a separate survey, which was used to collect a data set of self-rated skills, proficiency in skills from 316 GitHub users. In terms of evaluating Disco, what we looked at were the precision of the presence of having a skill, as well as the precision of having a high proficiency in a particular skill. So let's take a quick look at results. Overall, we find that Disco is able to, the skills that Disco surfaces are generally important to OSS contributors, where soft skills definitely take the highest importance. Furthermore, we find that contributors would publicly display these skills. But interestingly, the top skills were all technical skills as opposed to soft skills compared to the other finding. And then looking at the actual performance of Disco itself, we find that it's able to detect the presence of skills with high precision, but the proficiency of, when we look at skill proficiency, we see that the precision is more of a moderate level. So with regard to discussion, one point that we really want to emphasize is that Disco itself is a generally simple and intuitive approach that still yields moderately successful results in detecting OSS-related skills. The way is that we think that skills detection could be a really rich direction for other researchers to look into. For example, one impact of this field could definitely be enhancing existing software engineering and OSS experiences. For instance, we might enhance, matching GitHub users to projects, or even automatically assigning experts to pull request assignments. Additionally, future work could definitely look into defining weights for signals, using machine learning, or even interviewing OSS practitioners to see, which of these signals are important. Because right now, the way that Disco works, everything is weighted equally. So that was a very quick whirlwind tour through this work. If you have any questions, feel free to take a look at our full paper, which I've linked on the top right, or you can ask questions now or reach out later. All right, thank you.
Okay. Any questions for Jenny? Yeah, thank you. Nice presentation. Let's do claps. And so if you want to ask questions in the chat, make sure actually click on a question. So I think it's kind of easier, maybe easier to answer. So they have a special question, not just a message. Just a question. So anybody has a question for Jenny? So Jenny, I have a question. So do you see it's this tool be used more in like a professional development environment, or maybe at also academia, or maybe some doing open source development? So where do you think it's going to work better?
Yeah, I mean, I think, truthfully, I think this approach is rather a little bit more straightforward. And I think for it to be implemented in production, I think Using more sophisticated approaches like machine learning would probably be one really easy first step. But I think it could be easily integrated, as I mentioned, in existing OSS experiences. I think that's where I think this tool could really shine.
But there is some.
Yeah.
So we have a question from Marco and Igor too. So the first question, I can read it out also. Do you calculate the signals for a project or only for individuals?
Yeah, so we only calculate right now for individuals. We don't really look at anything at the project level, but that could definitely be allocated for future work as well.
Okay. Do you somehow consider expertise decay? It's a question from Igor.
Yeah, that's a super interesting question. We actually did not take that into account for this particular work. Although, especially because the way that we evaluate things right now is just by looking at particular snapshots of when we pulled out that data from. So theoretically, you could definitely build a profile of an individual's expertise over time. And one idea that we had is maybe instead of expertise decay, we were thinking expertise growth. So looking at how you can teach others relevant OSS skills over time through personalized coaching experiences or things like that.
Okay. Well, thank you so much. So if you guys have more questions, you can just type in the chat and Jenny will answer you there. So again, thank you so much again. So do we still have Michael Lane? No? Okay, so then we have can move to the last presentation. So Zach, I see you here. Can you share your screen? Can you start your presentation?
I think so. Can you hear me?
Yeah, I can hear you. So you can go ahead and set up your screen sharing, and I will introduce the topic. So Zach, I'm going to do poster presentation, deriving semantic aware fuzzers from web API schemas, right? Did I say correctly? Okay. Oops, I lost him.
Can you hear me now?
I can hear you now.
Sorry about that. Just some microphone issues, I think. And let's share my thing as well. So, my plan is essentially just to walk you.
We don't see your slides, unfortunately.
Can you see that now?
We see a paper, not slides.
Yep.
Do you want to just show the paper? Okay.
Yep. So my plan was to walk briefly through the preprint, and particularly with reference to some of the key figures in that. So my paper is on deriving semantics-aware fuzzers from web API schemas. So the core idea here is that I, and then later Dimitri, my co-author, have worked on property-based testing tools for a couple of years. And over that same period, there's been a real rise in the number of web applications, especially REST APIs or GraphQL APIs, which have some kind of well-defined schema. And so a natural thought for both of us was to go, well, if we know the schema, can we automatically derive a property-based test suite for this? That is, for each endpoint, make a request or a series of requests with valid parameters or invalid parameters to make testing this as powerful as possible with as little input from the user as we can get away with. And it turns out that this works remarkably well. So a quick intro, property-based testing is the idea that you can write tests which are in some sense quantified over some space of possible inputs. In Python, the most popular option is hypothesis. That's the one we both use. And so we built on top of that. The other key piece here is that the standards that we were using actually imply very much about the semantic properties of the API. For example, we know that an HTTP 500 status code always indicates that there was an internal server error. If it doesn't, then you have a standards violation, which is itself an error that we want to report. But if you go read the standards carefully, you can actually see a number of other ones. For example, a 204 response or a 205 response must have an empty body. A 302 must have a subsequent kind of relationship, and then there are a range of other ones. For example, if you delete something, then you can't get it subsequently. For the prior art, I will refer you to our paper, but there are many things in prior art. So Schemathesis has a command line interface, a Python interface for those who like writing Python, and most recently, Dimitri has also started an online web application. So you can literally just paste the URL for your application in and start testing it. Schemathesis also works with both single requests or sequences of requests according to OpenAPI links. And the basis of all of this is the Hypothesis JSON schema library, which takes the schema for allowed inputs and from that constructs automatically a precise and efficient generator of allowed inputs. For some things, this is fairly easy. If you have the schema for integers, then we can convert that to what we call a hypothesis strategy for integers. However, other cases are considerably more difficult. If you say that there's an object where you have additional properties of false, and you have a separate schema which has properties A, then this is actually an example of intersecting constraints. And so much of what makes Schemathesis more efficient than previous tools is that we're very careful to canonicalize the representations of these schemas before we translate them to data generators. This also means that we can very precisely and efficiently generate invalid data. For example, if the schema only allows integers in a certain range, we can generate precisely things of the correct type, for example, integers, which are outside of the valid range, or objects which are valid except that one of the string keys doesn't match the regular expression that's required of keys. That turns out to be quite powerful. Schemathesis is also customizable. So you can have custom hooks, serializers, strategies for custom formats like credit card numbers. All of these things are, I think, unusual for an academic paper, but turn out to be very valuable for our users in practice. Schemathesis was first developed as a production industrial system, then as a community-driven open source project, and then later we realized we were onto something and wrote it up as a paper. But you are probably kind of wondering, what kind of bugs does this find? Or at least that's the traditional question to answer for a fuzzing paper. So the first thing we did was we just searched Schemathesis, having found it. So that's kind of cool, but that's not much of an evaluation, of course. So we also did an experimental evaluation. We sat down and we worked out 17 or 18 different real-world OpenAPI schema-based web applications, and then tested each of them using 3 configurations of Schemathesis and a further 6 or 7 other tools. Our findings there, as you might guess from this chart, are that Schemathesis actually finds many more bugs than most of the other tools we dealt with. So these are unique or deduplicated errors. Schemathesis both finds somewhere between 1.5 to 4.5 times as many, but it's also the only tool to work on more than 2/3 of these services without some kind of internal fault. So it's kind of hard to judge what the average outperformance is when the pairwise outperformance is always substantial and sometimes sort of infinitely good, if only because the other tools couldn't work on these at all. We also find that this isn't really coming at the expense of runtime. So Schemathesis doesn't tend to run for longer than other tools. It's in about the same range of usually a few seconds to a few minutes. But being based on property-based testing tools does mean that we're much better at reporting a single minimal counterexample for each distinct failure. These are minimized with respect to Schemathesis and Hypothesis' own internal notion of what constitutes a distinct failure, but then confirmed with reference to Sentry, which is a popular testing tool or error reporting tool in industry. So our intention over the coming period is to really build on this as a reusable benchmark suite, which you can find on Zenodo and on GitHub, and then investigate, does this replicate more widely, and how can we further improve the tools? So thank you.
Thank you so much. Let's give a round of applause for Zach. Okay, so let's now move on to questions. Somebody has questions, you can ask if you're able to. Otherwise, you can just type using the question option on your right-hand side. So Zach has actually come out from more like practical aspect and now to the research paper. Interesting. So what prompted this tool?
It turns out a lot of people actually do have web APIs, and they don't like
Mhm.
writing tests because it's tedious.
Mm-hmm.
And so the goal really was just going, here is this problem that practitioners have every single day. How can we try to make that easier?
Mm-hmm.
Because there is very little more tedious than writing an application with 500 endpoints and then writing a test for every single endpoint that if you make a valid GET request, you can get the thing. If you try to post, you can't post unless you're authorized. That if you delete and then get, then you don't get the thing that you just deleted. And this was just ripe for automation. And so that's what we tried.
Awesome. Great. So anybody else have questions? Little comments? I definitely very useful tool. Okay, so, and I'm still missing, oh, thank you so much, Zach. So we don't have any more questions. So definitely, maybe you can post a link to your full paper if somebody's interested.
Can do.
So otherwise, so is still missing one presenter for C-Rust's paper, Michael Lean. And I still don't see him there. So anyway, I think with that we are done with the session. So thank you so much. And I think we have a bunch more live sessions right now, so maybe you can go and attend those. Otherwise, hopefully we'll see you in our second session and third sessions for the posters. So enjoy the rest of your virtual XC, guys. Okay, Nihal, I think we're all done. So I'm just going to leave the session then.
Okay.
So,
Okay.
because you know you need to leave the last one, but yeah, I think we're all done. Okay, thank you so much. Thank you.
Thank you.
Bye.
Thank you,
See you
Professor.
around.
Bye.